Ladies and gentlemen, good morning and welcome to this Onda for Education webinar focused on the use of the Onda DIAS platform for flood mapping applications. So my name is Mario D'Alessio and I work for Serco as business manager for the Onda DIAS platform. And today I'm here with my colleague Miguel Castro, who is our today's Earth observation expert. First of all, it is a pleasure for us to hold this webinar, so thank you for joining us. And our goal today is to show you how you can use Onda DIAS platform to develop your ideas for the forthcoming Copernicus Hackathon in Vicenza, or to develop any future projects you will be dealing with. I have already met some of you at the Ca' Foscari University of Venice in December when I held a presentation, an info session on Onda DIAS platform. If you missed that event, don't worry, because I'm going to introduce the platform again before going into detail with the application. So first of all, let's have a look together at the agenda. So I will briefly introduce the Onda DIAS platform, and then I will leave the floor to my colleague Miguel for, I would say, the most exciting part of the webinar. So you will learn how to access Onda DIAS virtual machines. You will learn how to access the data by using our catalog or directly communicating with our cloud environment. And then you will see how you can use the Onda DIAS platform for flood mapping applications. For the purpose of this webinar, we will be using a tool called SNAP that was developed by the European Space Agency. So we will quickly introduce the tool, and then you will see how you can use SNAP to process Sentinel-1 and Sentinel-2 data for flood mapping purposes. Then you will learn how to export your results, and we will have a questions and answer session, of course, and we can also have another question and answer session halfway during the webinar. So we said that Onda is a DIAS, but what is a DIAS? So DIAS stands for Data and Information Access Services. This is an initiative funded by the European Commission and managed in partnership with the European Space Agency. So why did they decide to invest on this? Well, because today we are very lucky that we have access to a huge amount of data coming from several sources, like, for example, the Copernicus program, which is the most ambitious Earth observation program of all times. So these significant volumes of data are creating, of course, great opportunities for all of us and for our planet, I would say. But at the same time, this huge amount of data is also creating important challenges for who wants to exploit this data and transform this data into information. So this is why the European Commission, in partnership with the European Space Agency, decided to trigger this initiative in order for the community to have this tool that would facilitate both access and the exploitation of the data. So what is Onda? Onda is a cloud-based infrastructure that enables you to develop applications and services in the cloud that are based on Earth observation data. So Onda is basically two things. Onda is data and cloud resources. So let's see the first pillar, which is data. So we say that we bring people on data because we provide free and open access to one of the largest archives ever built for geospatial data and information. Today it consists of almost 22 petabytes of data, so you understand that this is a very large archive. And it includes all the Sentinel missions, which are the main missions of the Copernicus program. So Sentinel-1, Sentinel-2, Sentinel-3, and Sentinel-5P. And today you will see how to process Sentinel-1 and Sentinel-2 for flood mapping purposes. And we also include other missions like Envisat, which is a NASA's mission, and Landsat 8, which is a NASA mission. And we also have some maps from the Copernicus services, specifically the marine, the land, and the atmosphere. So for a total of almost 22 petabytes of data. And these are growing datasets, meaning that every day we ingest the new data that is acquired by the active sensors, and we make it available into Onda. So growing dataset, we ingest every day terabytes of data. And the good news is that this is just the starting point, because you can add your own data or the data coming from other sources. And you can use this platform and this data to develop any type of application. So this is the first pillar. Let's go to the second pillar, which is cloud resources. Of course, we also have very high resolution data, so our users can also request very high resolution data up to 40 centimeters for both archive and new acquisition. And in our fleet we have both SAR and optical data. If you are interested, you can visit the our web order form in our website. Second pillar is cloud resources for you to develop your applications and services. So basically we provide virtual servers for any scenario. So you can design your own virtual server, your own virtual machine by choosing the storage, the RAM, the bandwidth, all the specifications that you need. And of course we also have pre-configured templates that you can find in our Onda website. So basically we have virtual machines, entry-level virtual machines, and also high performance virtual machines that you can use standalone, or you can organize in more complex systems. And you would get access to all the main advantages of the cloud technology. Also maybe the main one is the scalability, because you are able to scale up and scale down your system at any time. So you basically pay only what you use. Of course, you can install any tool that you want, of course open source tools, and if you have also licensed tools, you can of course install them. And you can also use your Onda infrastructure on a pay-per-use basis with a hourly rate, or on a monthly subscription basis with a monthly rate. So this is a very quick introduction of the Onda DIAS platform. Now I would like to leave the floor to my colleague Miguel for the most exciting part of the webinar. So you will learn how to use this platform for flood mapping applications. So I will be here for your questions. So Miguel, the floor is yours.
Well, thank you very much, Mario. Again, I'm Miguel Castro. For those of you that just joined us, I'm working together with the Onda team here in Cerco, and today I will be running the exercise with you. So, moving on after the introduction to Onda, now we're going to be focusing on the part of data processing. So, for that, I will introduce you first of all to the platform we are going to be using, to the Onda virtual machine, so that you can get an idea of how it looks like. So the first thing I want to highlight is how to actually access a virtual machine. So as you can imagine, this is done via the Guacamole interface, and it's very easy. Once you apply for the Onda virtual machine, you will receive the link with your private password. So, and this is something important to highlight, the Onda platform is completely private to the end user, so there is no way we can as service providers access your environment, and this is one of the key components that you have to think when working on the cloud. So you will access to the virtual machine. In this case, we are working on a Linux-based virtual environment, and this is one of the ready-to-use virtual machines that Onda is providing, as Mario explained. In this case, we are in this environment where we have already a predefined list of software installed, so that you can start your analysis and you can start to build your applications straight away. So once you get access, it's just a matter of you starting to play with the data. And we will see what are the advantages of having this cloud archive of Copernicus data already connected to the virtual machine, because this will save you a lot of time in terms of download. So in the virtual machine, basically, for those of you that are new to this kind of work environment, you can find everything you would find in your regular computer. It's just that we are based on the cloud and we benefit from the main advantages of the cloud. But as you could expect, we have the software ready to use. We have our dedicated internet browser that relies on the internet connection of the servers. You have your file manager, so it's everything very friendly, let's say. If you are coming from the IT world, you are, I guess, used to this thing, but if you are not, this is a very easy way to get to use the cloud as a tool for your projects. So once the environment is introduced, I want to focus now on the cloud archive that is available in the Onda platform. And by that, I mean to all the 22 petabytes of data that Mario was mentioning before, because this is one of the main advantages of working with DIAS. So in the virtual machine, you can find actually this data as an object storage that is attached, let's say, to your working environment. So in this case, you can find it in the file manager system of the virtual machine. You will find a specific folder that is called MNT. This stands for mounted data. It means that we are, via this folder, we are connected to an object storage where all the data is stored. So if you access this folder, you can see we have here the Copernicus data. The message I want to pass is that within the Onda VM, you get all the data and you can start to work with that immediately. So today we're going to be using Sentinel-1 data to run our exercise. And let me introduce you to the study case we are going to be using today. We are going to be running a flood mapping analysis over Mozambique, so in the south of Africa. And last year, at the end of in November 2019, there was a huge event. There was an intense tropical cyclone that was called Cyclone Idai, which was one of the worst tropical cyclones on record that affected Africa and the southern hemisphere in general. So this cyclone affected mainly Mozambique, Zimbabwe, and Malawi, and it left, unfortunately, more than 1,300 people dead and many, many more missing. So this Cyclone Idai was the deadliest tropical cyclone recorded in the area, and because of its huge impact, we wanted to see how the area was affected and what was the number of hectares that were flooded. And for that, we can use either Sentinel-1 data or Sentinel-2, let's say either SAR data, radar data, or optical data. And today we will be using the two of them, and I will highlight what are the advantages of using SAR and what are the disadvantages of optical and so on. So the first thing I want to do is to actually introduce you to the satellite we're going to be using, Sentinel-1. From the questions we were asking when you were registering for this webinar, we asked you if you had some experience or not with SAR. So from what I remember, some of you are beginners, some of you have already some knowledge in SAR. So I will try to give you, let's say, a basic explanation of this system and of the main processing steps that are required, because nowadays with Sentinel-1, with the Copernicus program, SAR data is very abundant. So if you want to run applications with Earth observation data, at some point you will have to use SAR data. So Sentinel-1 is the first mission of the Copernicus program. It was Sentinel-1A launched in 2014, and it's formed actually by two satellites. It is what it's called a twin mission. We have two identical satellites, and they are orbiting the Earth and they are separated in a configuration of 180 degrees. And why ESA decided to perform this configuration? The idea was to improve the revisit time of the mission. As you can see in the animation, by having 2 satellites, we double our capacity to acquire products, and in that way we reduce the time that is needed to get a new acquisition over an area. So we have Sentinel-1A and Sentinel-1B, and as I said, it is a radar satellite. It is actually a SAR satellite, synthetic aperture radar, and it's working on the C-band. If you are used to optical data as Sentinel-2 or as Landsat, you can think of the C-band as one of those spectral bands of an optical sensor. In optical sensors, we have many different spectral bands. In radar systems, we can only choose one specific part of the electromagnetic spectrum where we send the radiation. So in this sense, we are working in the microwave part of the electromagnetic spectrum, and in opposition to optical sensors as well, this is an active sensor. It means that we are actively sending radiation, sending microwaves down to Earth, and then the antenna is collecting the backscatter that is coming back from the interaction with the target. So don't worry if those concepts are new to you. We will come back to them while we do the exercise. Again, another key aspect to remember about Sentinel-1 in general is the repeat cycle. So this is one of the parameters that are more relevant when working with data. With Sentinel-1, you have a repeat cycle of 6 days at the equator. Sorry, there is a typo in the presentation. It's maximum 6 days at the equator. So if you go to northern latitudes or to the south, this number will decrease, and you can get revisit times that are much lower. And the last comment about Sentinel-1 is that since we are using an active sensor, since we are emitting the radiation ourselves, so the system is emitting the radiation, we can control the way the radiation is sent. And this allows us to play a little bit with this parameter and improve the type of image we are getting. So this is another key parameter when working with radar. So once the satellite is introduced, let's move and start our exercise. So before starting, actually, I want to highlight again, if you have questions, I would highly recommend you not to wait until the end or not to wait until tomorrow. Send us your questions as soon as you have them. There is a dedicated tab on the tool we are using today, which is called questions. So you can write there your questions, and we will come back to that as soon as we receive it. So, as Mario mentioned today, we are going to be using SNAP. So for those of you new to this, SNAP is the official Earth observation software that is supported by the European Space Agency, and it's, let's say, the official, not official, but the most recommended software to process especially Sentinel-1 data, and you will see now why. In the Onda virtual machine we are using, you can find a list of software that is already installed, and in this case, SNAP is part of that list. You can see also other GIS software like QGIS, and also developing environments like Jupyter Notebooks, Anaconda if you want to build more specific applications, etc. Of course, Python is also available. Anyways, this is the SNAP software, and for those of you new to this software, I will give you a very basic introduction. It is very friendly to use, and it is very graphical, let's say. It is divided in 4 main areas. The main one is this product explorer, where we will see the list of products that we are working with, and you will see how this populates later on. Then in this lower left corner, we have some quick menus like navigation, world map, color manipulation, and this will allow us to interact with the data for some specific features that are very handy to have a quick access to that. Then we have the main display area, which is this very black, this gray area that you see here. This is where the image will be shown, and we will do this in a few minutes. And then the other part of the software are the tools. So basically you have all the tools in this bar here, but also in the dedicated menus on the upper bar. So the tools are divided basically on the type of data. So for example, if we are working with vector data, there are several tools here. If we are working with raster, well, you can see, for example, geometric operations, data conversion, classifications, etc. And then if we are working with optical or radar, we have different tools. So well, you can imagine here you can find a long list of algorithms that are used to pre-process and process optical and radar data. So the first thing we want to do to start our exercise is to load our data. So for that, I'm going to open the images we're going to be using today in Snap. So you can go to File, Open Product, and I have them in a specific folder. And now I will explain you where's the cloud data. So those are the three images we're going to be using. They are Sentinel-1, in this case A and B. You can see here on the name S1A and B. And then you can see here the acquisition date. So this is from March 2019. So I was telling you that one of the advantages of Onda is having the cloud archive already available in the virtual machine. And I was trying to show it to you before. Now I think it's more convenient. So as I said, this data is available in your virtual machine in a specific folder that's a connection to an object storage, which is called mounted, MNT. So if you go to the Copernicus folder, you will access a long list of folders that, if you're new to this, seems like a little bit random, but it is not actually. Those are different paths, different relative paths that you can follow to actually get to the images. If you think about what Mario said, we are working with a huge archive of like 20 petabytes or so. So you must follow a structure to access a huge amount of data. For example, if you're looking for optical data, you can go via the optical folder, but if you know that you want Sentinel-2 optical data, you could also go via the Sentinel-2 folder. This doesn't mean that there is a duplicate on the product. Those are only different paths to reach the final data. So don't think that we have different folders that contain the same data and we are wasting resources. It is not the case in Onda. So, for example, if you are interested in Sentinel-2, let's say you go via Sentinel-2 folder. That would be the right move. And then you can select different options. Either you're looking, for example, for a Sentinel-2A or 2B product. Either you are looking for you are interested in the level of the product, so either 1C or 2A. Well, those are different parameters that when you start to work with the data, you will know much better. So let's say we want Sentinel-2 data that is atmospherically corrected. In that case, we would go to level 2A, and then we would select the instrument, in this case Sentinel-2 multispectral instrument, and then it's just a matter of selecting the specific acquisition time you're interested on. So for example, we can go to 2020, January, and this is just, let's say, like a calendar. Then it gives you all the days of the month. For example, we can go to the 20th of January, and now the system is loading all the products that were acquired by the satellite that day, and you will see that in a few seconds this folder will be populated with thousands of products, and it is then up to the user to find a way to locate those products in the folder. So what I mean is you need to know which is a product of interest so that you can retrieve that product from the cloud and start to work with it. So I will just wait until this loads so that you can see the folder. But in the meantime, I want to introduce you to another tool that is available. So, okay, let's first of all talk about this. As you can see, we have almost 9,000 products, 9,000 Sentinel-2 products that were acquired that day by the satellite. And they are available in the Onda virtual machine to the user so that you can start to work with the data. And those are images that are already present here. There is no download process required. So I will demonstrate that. If you go to the folder and you access the product, you can see that you can reach the actual measurement done by the satellite. You can reach the, let's say, JPEG raster that contains the measurements. So you can see it here. So those are the bands of the satellite. And this is something that is already in the virtual machine that you don't need to download. You could, for example, take this file into Snap, into QGIS, into Python, into whatever, and start to work with that. So you can see that the only thing that you need when working in Onda is to build a way to access this data in an automatic way. Of course, you can do it manually if you're only interested in running an analysis with one image. But if you want to run an application in an operational way where you want to process images constantly, then it's up to the user to build a system that retrieves the data automatically and runs a specific algorithm, for example, float mapping. So one of the things we get from our users is that when retrieving the data, of course, the first question that can come to you is, how do you know which image out of those 9,000 images is your specific image? So for that, in Onda we have a little tool that we developed to make this process a little bit easier to the user, and I want to introduce this to you. It is available in the Onda virtual machine. We call it Onda Data Finder, and what it does basically is that it asks you if what it will do is it will locate in the cloud archive the image of interest. So let's say we want to look for the image that we are going to be using today in our exercise. I have here the name of that product. So let's say you have this image here. How can you get this specific name? Well, you could, for example, do a query, a graphical query in the Onda catalog. So let's say you go to the Onda website and you go to the Onda catalog where all the products are available in a graphical way, let's say. Here you could, let's say, run a typical data search. For example, let's do it. You could just, well, for example, over here, we can select Sentinel-2, and we can select a specific acquisition time. So let's say this would be standard procedure when looking for products. So 1st of January, and let's say until today. And now we define our area of interest. And now it is looking for the products. No, sorry, I didn't click the search button. Let's do it. So when doing so, you would get those are the products that match our query. And of course, this is just the catalog. So here there is no direct access to the data. But what you can do, for example, is to copy paste this name and then go to the tool that we have developed so that you can locate that product on the cloud. In this case, I'm showing you for Sentinel-2. Let's do it for Sentinel-1. So that would be, let's say, the way to get that product name. So in this case, we are interested in a Sentinel-1 product. So you could copy paste the name of the product. And then if we use the tool that is here, we can just copy paste the name. And it will send this request to the Onda catalog via the API, the public API that is available for users of Onda. And it will check that the product is available on the cloud, and it will tell you in which directory you can find that. So you can see here it's telling you that the product is available in this specific folder, and it's actually asking you if you want to open that folder so that you can see the data. So you can you just need to reply true, and immediately the system will open the folder where in the cloud data, in the cloud archive, where you can find the product. So this is the product, this is the measurement, those are the geotiffs in the case of Sentinel-1 that contains the measurements that were done by the satellite. And again, I want to highlight the fact that this is ready to use. There is no download process at all, and this is a quick search into the cloud archive. So there are different ways to use the tool, and another option would be to import instead of one image. Let's say you have a case where you want to locate different images at the same time. So in this case, the tool also allows you to import a specific file that comes from the Copernicus Open Access Hub, which is another catalog of Copernicus data. I will not go into that, but the thing I want to highlight is the flexibility that you have on Onda to build your own solutions, let's say. So you have the data, you have the software, it's up to the user to design the way to find the data and build its own application. This is just an example where we show the potential of what you could do. So for example, if you are interested in different images, you could insert this type of file that contains information about the products of interest. And again, this is coming from the Copernicus Open Access Hub. And basically what this will do, it will read this file, which is an XML file, but it could also be a TXT, for example, and it will locate all the images that were identified and ask you if you want to open a snap session. So you can just say true, and then a snap session, which I will introduce now, will be created. In addition, it asks you also if you want to open one of the products, if you want to see the folder of one of the products. So you can just put its index. So you see here 1, 2, 3. So if we type 3 here, it will open the folder and you will see it. So let's wait, it's loading the folder. In the meantime, let's move on. So that's how you can access the data in the Onda platform. That's how you can, let's say, search into the cloud archive in a more manual way by just, let's say, exploring the folder, or by building or using a tool that allows you to take immediately what you want from the cloud archive. So in our case, we want to process these 3 images, and those are Sentinel-1 images. So if I open one of them right now to see how it looks like, you will see that there is actually a lot of processing that has to be done. And for that, we're going to be running a processing chain that contains the different algorithms that are needed to pre-process our data. Okay, so here we see the image. If you're new to radar, you will see that this looks completely different to what you could expect in optical data. By the way, you can see here on the map the location of the product. We are in the south of Africa, so we're in Mozambique. This is the area, and this is the footprint of the 3 products. So you can see that the image looks very different. If you are new to radar data, it's hard to see any pattern. And if we zoom into the pixel level, there is even more confusion because it seems like a random noise, let's say. This is, well, this is how radar looks. But of course, one of the differences between radar and optical data is that before using the data, we need to run some pre-processing. With optical data, you take the image and you can start to run your analysis straight away. With radar, we need to run some processing steps that I will introduce you very briefly. However, I want to highlight something that is very obvious from this image. And it's the fact that you can see, let's say, a noisy area, which is the land, but in water, you can see that it's completely black. I mean, there is some what we call speckle, but it is very obvious that water can be seen in radar very, very easily. And that's why radar is a very good data source to run a flood mapping analysis, because water is very easily, you can very easily distinguish between water and non-water. This is due to the backscatter mechanism that takes place, but I will not go into that, not to give you too much information, seeing that you're new to radar. So for example, we see, of course, the ocean, you see the river over here. So you can see already the potential of the data. So how are we going to process the data? Well, you can follow 2 approaches. The first one would be to run every step individually in every product. Let's say I select my product, I go to the radar, I select the algorithm, and I produce an intermediate step, and then I move on and so on. This, of course, is not very efficient from the point of view of processing and storage, because you will be using a lot of processing time, and you will be building, or you will be creating intermediate steps that are actually not needed for yourself. It's just an input that has to be produced for the next step, and so on. So there's no need actually to do, I mean, you could do it, but it's not very smart, let's say. So luckily in Snap, there is a specific tool that allows us to chain different algorithms together. And this is something very common in other softwares. If you are used to, let's say, QGIS, even ArcGIS has this kind of graph processing tools. So nothing very different from other softwares that you might know. In Snap, this tool is available in Tools, and it's called Graph Builder. And Graph Builder will allow us, as I said, to build this chain. So I will explain you the different steps that are required, and you can think about the chain I'm going to introduce you as the standard pre-processing chain that you have to apply every time you need to process Sentinel-1 data. Of course, there are some differences between one application and another, but most of the steps I'm going to explain you right now, you could think of them as the procedure to follow whenever you need to use SAR data for any application. So, seeing that some of you are new to Radar, I will not go too much into the details of every step. Of course, I will give you an explanation so that you can understand the idea behind. If you're interested to know more, I recommend you to Google for SAR theory books and literature, where you can find the explanation of every step more in detail. Anyway, the first thing we have to do when processing SAR data, and let's say a good practice to do, is what it's called the update of the orbit. Since we are using an active satellite, since we are sending our radiation, it is very important in this context to know what was the position of the satellite at the moment the measurement was done. And this information of the position of the satellite is retrieved by analyzing the orbit that the satellite was following, right? So the orbit, the information about the orbit, it's something that is sent by the satellite together with the measurement. However, a couple of weeks after, once the satellite has gone through the orbit several times, ESA can, let's say briefly, can know exactly and very precisely where was the satellite at every moment. So they do some post-processing of the orbits, and they know a couple of weeks after exactly with a lot of accuracy what was the position of the satellite in a 3D space. And this update of the orbits is a fundamental step in some applications more than in others, but I think it's good practice for you to know that it is relevant to update those orbits. Luckily, in Snap, there is a specific tool that does this automatically, so we don't have to worry about anything. The only thing you need to do is to add this step to your processing chain. So in the graph builder, we have first the read operator, and to add another step to the chain, we just need to right-click and go to the specific path where this tool that we want to use is located. In this case, we need to go to Add Radar, Apply Orbit File. So this is the tool that will automatically connect to the database of orbits that it's hosted by ESA, and will retrieve the most recent information and apply it to our product. As you can see, when I add an operator to the graph, there is a dedicated tab that pops up in this lower part. This is where you can set the parameters for that specific step. In the case of apply orbit file, there is nothing to change, so you can leave the default parameters. The only thing I would recommend you is to click the option do not fail if your orbit file is not found. What does that mean? It means that when requesting the orbit, if there is any error on the database or wherever and the orbit is not available, we are telling to the processing chain that it must not stop, and it must continue with the processing. Why? Because while it's relevant to update the orbit, it is true that for this specific application it's not completely necessary. It is good procedure, but you could run it without it. So we select this option to avoid any failure in our processing chain. So this is the first step we are going to run, and this will not update the pixel information. This will not change the measurement done by the satellite. It will only change the metadata of the product. The next step we need to run is called thermal noise removal. So let me add it first, and I will explain you what it means. So we go to Add Radar, then we go to radiometric and thermal noise removal. So this specific step is relevant, especially when working for water applications in radar. And I will explain you a little bit why is this necessary. You have to think about the radar system as an active system, right? It means that we are sending radiation from the antenna, and maybe I can go to the animation. So if you see here the video, you see this green light going from the satellite to the Earth. This is, let's say, a visualization of the radiation we are sending. Because we are sending radiation, because there are some electronics on the satellite, some power on the antenna, there is some inherent noise, there is some background noise due to the fact that we are producing power. And this is something that the sensor that measures back the radiation is also measuring. So it is important to remove that noise, that bias on our measurements. But this is something very easy to do because the satellite, before being sent to space, it is calibrated by ESA, right? So they know very well the characteristics of the system, etc. So they know very well which is the amount of power that is being introduced by the fact of generating power to be sent to Earth. So to remove that, we add the step thermal noise removal, and in the parameters of this operator there is no need to change anything. The only thing we leave as default the fact of removing the thermal noise. So those would be more the first steps, and the next one is actually it is mandatory to run when running SAR applications. So the next one is really mandatory and important. It's called calibration. So let me first of all add it. So radar radiometric calibration. So what is calibration in SAR processing? Well, the objective of SAR calibration is to provide images in which the pixel value can be directly related to the radar backscatter of the scene. What do I mean by radar backscatter? Radar backscatter, it's, let's say, the amount of radiation that comes back from the target to the satellite. So we send radiation to an area, let's say to a pixel, like an area that is represented by a pixel, and what we need to do is to relate the amount of backscatter that is coming to the size of that pixel. Again, I will not go into the details of this. You can find the references very easily, but you need to understand that when working with SAR data, we need to calibrate the image so that we have a measurement of the amount of energy that is coming from the area represented by the pixel. So there are different ways, there are different calibrations, there are different parameters. Again, not going into the details. What you have to remember is that the one that is most of the times used in any research is the parameter that is called sigma naught. If you look for SAR literature, you will see this word popping up a lot. Sigma naught is the same as saying radar backscatter coefficient. So again, you can take this as granted. We leave the default parameters, we just calibrate the image, and we produce our sigma naught band. So you can see in the original product, what we have is amplitude and intensity. If you are familiar with electromagnetic waves, those are, let's say, the main parameters of an electromagnetic wave, right? The intensity, the amount of power, and the amplitude. So when doing calibration, we are moving those measurements into the sigma naught variable. And again, sigma naught is the amount of radiation that represents, that comes from the area represented by a specific pixel. So this would be our first fundamental step. And after that, we go into another very important step in SAR preprocessing, which is the speckle filtering. And what is speckle in radar? Well, if we go to the original image, and if I zoom in into the pixel level, you can see this completely random behavior, right? We have white pixels, we have black pixels, and it seems like complete noise. And in fact, there is a huge part that is noise in the measurement that the satellite is making. And this is due to the fact of using an active sensor. Again, let's leave the explanation there. But speckle is this noise that is introduced by the system itself, by the nature of using an active system, in which we have what it's called a coherent return. It means that when sending radiation to a pixel, to an area, the radiation is going to interact with many elements within the pixel, right? And there is going to be backscatter, there is going to be a backscatter of radiation coming from the different elements of a pixel. Let's say in a pixel we have a rock, we have grass, and we have a tree, and all is within a pixel. When we send radiation, there's radiation that is going to hit the rock, and then it's going to go back to the satellite. But there's also going to be radiation that is going to hit the tree and go back to the satellite and so on. And this amount of the radiation, it combines together and it reaches the satellite. And this is completely random. There is no way to know how this happens exactly. So in one pixel, it will happen in one way. In the pixel next to it, it will happen in a completely different way. Even in the same pixel and at different times, it will happen in a completely random way and different. And that's why you can see these images of these radar images where one pixel has a specific value, and then the pixel next to it has a completely different value. If you think about optical, which is not actually a very good idea when interpreting SAR images, but just to make a comparison, if you think about an agricultural field in a Sentinel-2 image, in an optical image, you will see the agricultural field homogeneous. Let's say one pixel will be very, very similar to the other. In radar, that doesn't work because of the way the radiation interacts with our target, right? So I'm telling you this because, as I said, there is this noise on the image, this speckle, it's called speckle, and there are different ways to correct. It is important for you to understand that the speckle noise of a radar image cannot be removed. So it is what it is. It cannot be eliminated from the image. What we can do is to reduce its effect. And that's why on our processing chain, we are going to add a step that is called speckle filtering. So let me go to radar, speckle filtering, and speckle filter. So here's the tool. Again, if we go to the tab of speckle filter, you can see here it's a little bit more complicated. There are many parameters, and those are just different algorithms that can be used to reduce the speckle. So again, there's no need for you to understand speckle filter is a huge domain in SAR. There are many variations of the different approaches that are used to reduce speckle. So what you have to know is in SAR images, there is speckle, and we need to reduce it by using speckle filter. There are many speckle filters, but in this case, we're going to use the one that is selected by Snap by default, the Lee Sigma filter. It is actually a filter that you will see in literature very commonly used. So it is kind of standard procedure. So this we leave as default. And now we go to the last part of our processing chain, which will correct our product. So the next step is called in radar terrain correction, and this is going to be easy for you to understand. When we have the image, we need, of course, to project this image into a specific UTM projection, into map coordinates, into geographical coordinates, or whatever your application requires. So because of the nature of having an active sensor, images are not projected into a grid. So we have to do this step. And for that, we use a tool that is available in Snap. And you can see why Snap is so relevant when working with Sentinel-1 data, because it has all the tools you need to run this pre-processing of the data that is completely mandatory if you want to use the data for, in this case, flood mapping. So we go to radar, geometric, and terrain correction, and we select the algorithm terrain correction. So what is going to happen here? The image is going to be reprojected, and if we go to the terrain correction tab, you can see there are many parameters, and one of them is the map projection. So you can actually select the projection you want to give, in this case WGS, but you can also select others. I mean, there's a huge list of projections. I personally prefer to project things in UTM, so I select UTM automatic. It means that the software will automatically recognize the UTM, the UTM zone in which the product is located, and it will apply the parameters for that reprojection. So in this case, the software recognized that this image is in the UTM zone 36 south. Then the other component of this algorithm terrain correction relies on the different terrain distortions that happen in radar. Again, I will not go into that. I will briefly comment what does that mean. When working with radar, there are different terrain distortions. It means that we are sending radiation, and because we are using a system that is not looking in the nadir direction, the nadir direction means that we are looking from a point of view that is completely vertical to the satellite, it's perpendicular. In radar, we are using a side-seeing satellite. It means that the satellite is looking to the right side or to left side. In the case of Sentinel-1, is the right side. So because of that, again, I refer you to SAR literature. There are different distortions caused by the terrain, by the topography. So we have mountains, we have different effects that will change a little bit the geometry of our image. And those distortions have to be corrected. Luckily, the terrain correction algorithm will do that for us, and it will do so by using a digital elevation model as reference. So this is all I wanted to say about this. Again, if you want to know more, I refer you to the literature of radar. I'm going to remove this option, mask out areas with elevation, just to avoid the fact of the image being clipped to the land area and not having the water surface. So I'll just remove this. Okay, so once we have the terrain correction done, we are ready for the last step of not the last step, the one before, which is going to be a transformation of the data. We are going to be using a decibel transformation. So if you are familiar with logarithms in general, you will know that decibel is just a logarithmic scale, and that is used a lot to reorganize a little bit the data. So when you have a data distribution that is not homogeneous, that doesn't have a normal distribution, etc., it is good to apply a logarithmic transformation, in this case the decibel scale, so that the data is a little bit more homogeneous, let's say, in its distribution. So again, the important thing of the decibel transformation is to know that we are not losing the original measurement done by the satellite. If you remember your math class, you will know that when applying a logarithmic transformation, you are not losing the original data, because you can basically undo the logarithmic transformation and get your original value back. Why are we doing this in SAR? Because in SAR, the distribution of the data, if you look at the histogram of the image, it doesn't have a normal distribution, and this affects your ability to distribute colors in an efficient way, and then affects your ability to see patterns in the image. So it is better to put everything into a decibel transformation so that we can have a better visualization. So decibel transformation is mainly done to improve the visual recognition of patterns in the image. That's the key message. So how do we do this in Snap? We right-click and we go to raster, data conversion, and linear to from decibel. This is the tool. So let me make this bigger. And I was checking actually if you have some questions. I see you have no questions. So hopefully I'm explaining myself very well. But if not, don't be afraid. Please use the chance to ask all the doubts about SAR, about Onda, about the VM, about the data, about Copernicus. Just highlighting that. Okay, so we go back to our graph. So we connect the two algorithms, and in the parameters, there's nothing to change. It's just a decibel transformation, so nothing to change. So the very last step, the very last one, will be a subset. So there's not a lot to explain. We are just gonna clip our image to a smaller area so that we save processing time. You have to think that radar data is very heavy compared to optical data. So if you can save processing time by reducing the spatial extent of the product or by any other means, it is highly recommended. That's why we put the subset operator. So let's first add it. So we go to raster, geometric, and subset, and we connect the operator. In the subset tab, you can see that you can do two types of subsets. Either you select you do a subset of bands. So you say, I only want to carry on with one of the two polarizations. I will explain you what this VVVH means now. And the other thing you can do is a spatial subset. And you can do so by specifying pixel coordinates or geographical coordinates. I think it is more convenient to use geographical coordinates because it's just a matter of going to this map, zooming into the product by clicking on this button, and then you can just draw your region of interest by right-clicking on the map and, let's say, drawing your area. So this is going to be our subset area. So you see, very easy, nothing to comment. So now the question I get very often when I do this is, why am I doing the subset at the very end of the processing chain and not at the beginning? If the idea of the subset is to reduce the processing time, wouldn't it be better to run the subset first of all, so that the other steps can beneficiate from the fact of working with a smaller product? This would be actually a good point and completely logic. However, in Snap, it is good to know that when running a graph, the system will check all the requirements of your graph. And it will see that there is a subset operator at the very end with a subset area. So the speckle filter, the calibration, the terrain correction, all those steps will only happen in the area we have identified in our subset. So it doesn't matter actually if you put it at the beginning or at the end. The actual processing will only take place in the area that you have designated. So I personally prefer to put it in the end, but feel free to put it wherever you want. So that's for the subset, and the very, very last step will be, as you can imagine, the write operator. So once we read our product at the beginning, we apply all those steps. The last thing we need to do is to write the file itself. And for that, we just add the write operator. And in the write tab, you can imagine you can put the output name and the output directory, and you can also change the format. Snap has a long list of formats available: GeoTIFF, JPEG 2000, long list. However, I would recommend you to leave the default format, the BIMAP format, which is the standard one for Sentinel and Copernicus data. So this is the pre-processing chain you have to apply to Sentinel-1 data, I would say most of the times for any application. So you see, today we are doing flood mapping, but if you were doing urban mapping, for example, this would be most probably the same chain. There are some specific parameters that maybe are better for one thing or the other, but in general, it's okay. So what would be the next step? Well, we have defined the processing chain, and we have defined one image to be processed. So if you go to the read operator here, you see I want to pre-process this first image. However, if you remember, I have 3 images in total. There's one image before the cyclone, then one during the flood, and one after the flood. So you could potentially run this graph for the first image, click the run button, and wait. Then change the input manually, run the graph again, and so on. And then the third and the fourth, and imagine you have 20 images. It's going to be a waste of time. Luckily, there is a way to automatize this in Snap, and this is very, very convenient if you are working with several images. This applies for Sentinel-1, for Sentinel-2, for Sentinel-3, and you can do that. You can do this that I'm going to show you now for every mission. So the first thing you have to do to automatize the processing is to save the graph. So here's the graph. So just save the file. So you can, for example, save it in a folder of your virtual machine. I'm gonna leave the default name mygraph.xml, and I just save it. Once saved, you can close this because we're done. Now we are going to open another tool in Snap that is going to allow us to do this automatic processing of several images. Sorry. This is what we call batch processing. So if you go to Tools, Batch Processing, here's the way to, let's say, in a friendly way, automatize the processing. So the first thing you have to do is to define which are the images you want to pre-process. And you can do so very easily by clicking on the plus button and then navigating to the folder where you have the products. Or if you have them open in Snap, you can click on this other icon here, and this will automatically upload all the images that are open in Snap into the batch processing tool. So you see, those are my images. And I can also refresh the metadata by clicking on the refresh button. And then this will give you just information about the type, acquisition, etc. So basically that's all. So once we have defined the input products we want to pre-process, the other thing we have to do is to say, okay, those are my inputs. Now I need to define the processing chain I want to apply to those inputs. And it is here where we are going to make use of the graph we have created before. So first of all, we remove this option, keep source product name. And this is very important. I want to stop here. Later on during the hackathon, if you are using this tool, it is very important that you remove this option. Why? Because if not, every time a new product is processed, it will get the same name. So you will be overwriting your final output every time. So let's say you are processing 10 images. In the end, you will see only one output. It's not that the process failed, it's just that it was overwriting with the same name the output of every iteration. So remove this option and then load the graph. So to load the graph, I'm going to use a backup graph that I created in advance. It is basically the same as the one I have created with you. The one I have created with you, it's here. I'm just going to use the backup to avoid any error. So when you load the graph, you see now that all the algorithms that we defined in the graph are present here. So you remember apply all with file, thermal noise removal, calibration, etc. So now you could change any parameter if you would like, but if not, the same parameters that we have selected before are set here. So what I recommend you to do is to quickly check everything. So apply all with file, make sure that everything is as you would like. Speckle filter, we leave everything as default. Terrain correction, we change the map projection, so that's good. Linear to decibel, we don't change anything. And in subset, we have the region of interest. You can click on this icon to zoom in, and here's our region of interest. Okay, and then the right. So, what would be the procedure now? Once you have the inputs defined and the processing chain defined and everything saved, the outputs are going to be saved in this folder that we have specified. So if you want to change the folder, it's up to you. So it is important to remember that folder because later on it's here where we have to go to open those products. So once you have this, the only thing you have to do is click the run button. So now I'm not going to run the process, because although we are working on a cloud environment that is actually quite powerful, the virtual machine I'm using today for reference, it's the B230 Onda model, in case you're interested, in case you want to refer to this later on when asking your environment. This is a 32 gigabytes RAM virtual machine, which I would say from my experience, it's pretty good for processing of SAR data. Of course, the more RAM, the better, of course. But at a certain point, you have to balance resources and other things. I think this model, at least from my experience of processing heavy data, works fine. So anyway, even if we are working in a powerful environment, this would take several, I don't know, I think it was like 20 minutes or so. So we are not gonna be here waiting for the process to finish. There's no point of wasting the time. But I just want to let you know that the procedure will be to click on the run button and basically wait. What will happen afterwards? Well, I'm gonna close this window here. So the products are processed in and are saved in the folder we have defined. So what we need to do now is to open those outputs in Snap. And to do so, it's the same as we did before. We go to File, Open Product, and we navigate to the folder that we have specified. In this case was the processing folder. Well, you can see here I have more data. So this is the backup data. So this is the data I processed before. Basically, you can see these are the outputs. And because we are using the bin dmap format, you have to know that if you don't know this format, just to give you the reference, this format produces a folder where all the measurements are stored, and then a .dim file, which is actually an XML-based format that points to the data. So when opening the data, I'm saying you this because when opening this kind of format in Snap, you have to select the .dim file. If you click on .data and open, it will give you an error in Snap. So remember, you have to select the .dim. So I select, those are my three outputs from the graph. I'm going to open them in Snap, and let's see now the output, how it compares to this very first original image. So this was the, I'm going to show you actually, this was the image before the flood, so that's why we don't see any flooded area basically. I'm going to open the image during the flood, which is the one from March 19. So this is the original image of that day. So now it's loading in Snap, and we will look at it, and then we will see how it compares to the image that we have pre-processed in Snap. So here we have the original image, and as you can see, the flooded area is very, very obvious. I told you before that water is something that can be seen very, very well in SAR imagery. Urban areas can also be seen very easily in SAR images because they have the opposite to water. They have a very high backscatter, for example. If I go here, well, this is obviously water. This is the river. This is the flooded area, which is black. And all these very white spots are buildings, basically. So just to let you know that urban areas are also very easily distinguishable in SAR imagery. By the way, as a small detail, of course, it's very easy to know those are ships on the water. And now you can think about another application that with SAR works very, very well, and it is actually used by many governments and international agencies, etc., which is ship detection. You can see that water is very dark. Ships produce a very high backscatter, so they can be identified very, very easily. Anyway, this is the flooded area. As you can see, it was massive. And let's see how the output of our processing chain in this image compares. So we go to bands and we open the VV band. So actually now I forgot, I didn't mention what VV and VH means. For those of you new to radar, there is a concept in radar that is called polarization. Polarization means the orientation of the electrical field of the electromagnetic wave, if it's vertical or horizontal. Anyway, in a few words, what it means is because we are sending radiation with radar, because it is an active sensor, we can choose the orientation of the wave. We can, with a small device, we can change its orientation. So it can be vertical or horizontal. When we say VVVH, it means that we send the radiation as vertical, so that's the first V of the name. Then the radiation interacts with whatever, and it comes back to the satellite. When it comes back to the satellite, the electromagnetic wave can be either vertical or horizontal, and that's because of the interaction with the target. When the wave reaches the target, depending on the target, the orientation is going to change. And you can then in the satellite say, okay, I send in vertical and I only want to receive in vertical. Or the other way around, I send in vertical and I want to receive in horizontal. And this is one of the few parameters you can play with radar because we don't have spectral bands. So we have polarization channels. And again, if you check for literature, that will see that polarization gives you a way to know a little bit more about the target, because some targets change the polarization, some others they don't. So okay, just a small comment here. Anyway, for flood mapping, it's not that relevant. So here we see the result. So as you can see, first of all, when I change from one image to the other, you see that although this is a subset, it looks bigger than the original image, which is definitely larger in spatial terms. Of course, this is the result of our reprojection. We have moved from radar geometry into a UTM grid, so that's why they don't match spatially, for sure. We have done the subset, we can see here. We have reduced a little bit the speckle, so you can see that. And again, I told you, you cannot remove speckle, so there is still this kind of random behavior in the pixels. If you go to the pixel level here, this is the original image. You see it is very dramatic here, the changes. In the new one, it is not that much. I mean, there is still, but it has been reduced a little bit. Then we can see the consequence of using a decibel scale, because the data, I mean, from a visual perspective, it is much, the contrast, let's say, in the colors is much higher, right? Actually, if we look at the histogram of the data, you can see the distribution of the colors, etc. So, this is the output of our processing graph, and now we are ready actually to start our flood mapping analysis. We have our original images, we have run a basic pre-processing step, and now those outputs will allow us to run the flood mapping analysis. Looking at this image, if you want to give this information to a decision maker, for example, a crisis management or whatever, well, you see it is very obvious where the flooded area is. However, we can still apply very basic techniques that will allow us to better identify this flooded area. So the first thing we need to do is to create a raster stack. A raster stack, for in case you don't know, is just, let's say, a file that contains different rasters, different images that are stacked one on top of the other. And this way of managing the data, this way of creating a stack, will allow us to do very basic analysis for flood mapping. So anyway, it is very easy to do a stack. We can go to radar, co-registration, stack tools, create stack. There are different ways to put images together. One is create a stack, the other one is co-registration. And depending on your images, depending on your applications, you will use one or the other. In this case, we are using images, just for the record, I'm saying this, that have the same acquisition geometry. It means that they have been acquired in the same with the same viewing orbit and with the same look interaction, etc. Anyway, what I want to say is the images have the same geometrical characteristics, and that's why we can just stack them without co-registering them, because the images are, I mean, the orbits are very well controlled by ESA, so that the images that are acquired with the same acquisition geometry can overlap very well. If you would be combining images with different acquisition geometries, then you would need to co-register them. It means that you need ground control points so that you can basically match one pixel in one image with a pixel on another image, right? In this case, the create stack is going to work just fine. So again, we have this menu. We use the same way. We take all the images into the create stack, and we refresh the metadata. However, pay attention here. We don't want to stack the original products, because those actually are not needed anymore. So we select them and we say minus, we just remove them. So we want to stack the three outputs. So this is the input, then we go to the second tab, and here we are going to use, first of all, the resampling type. In theory, you would not need any resampling type because the pixels overlap very well. However, I think it's safe to at least put the less disruptive resampling algorithm, which is nearest neighbor, just in case there is a very little movement in the pixels, which will not happen, but anyway. But you could put none. Then for the initial offset method, we are going to be using product geolocation. So what's the option here? The system is asking you how you want to reference spatially your product. Do you want to use the orbit information to locate your image in space, or do you want to use the product geolocation? Since our images have been already terrain corrected, since they are already in a UTM grid, we prefer to use product geolocation. It's going to be more accurate than using the orbits. So product geolocation. And then we can just click the find optimal master just to, just to have the best fit for the master product. Remember, when doing a stack, there's going to be a master raster, and then there's going to be slave rasters that are going to match the projection of the master, right? And then in the third tab, we just, as always, put the output name and output directory. In my case, I'm going to change the name to stack. I think it's much easier. And I'm going to leave the default format and the default output. This process is very fast. We can run it together. I'm just going to change the folder to avoid overwriting my backup data. So we can just click the run button and it will start. So while this finishes, let's see if there is any question from your side. Very quickly checking. Okay, I see no questions. So in case you have any question, again, I insist on that. Actually, if you have questions and you want to ask them in Italian, feel free. We will answer you. It's no problem. So, okay, here we have the process finishing. And once we have the raster stack, we will be able to run our first flood mapping analysis, which is going to be a very basic multi-temporal RGB composition. So you will see it right now. Let's wait for this to finish. A few seconds more. A few more seconds. Okay, finished. You see, it took 1 minute, and now we can close this. So let's close the first 3 products that we don't need anymore. And now let's have a look to the stack. So if we go to the product and we go to the bands folder, we can see the result of the stack. You see, in one single file, we have the master raster, which was the image from the 19th of March. And then we have the slave 1 and slave 2, well, I mean 1, 2, 3, 4, for the other images. And you see we have all the polarization. So since we want to do a multi-temporal RGB composition, it is required to do a raster stack. Why? Because if you want to combine different bands from different images into one single visualization, you need to have those images in the same files. If not, it's not going to work. So in Snap, you can create an RGB composition by right-clicking on the product and selecting Open RGB. Then you can basically select which bands are going to go into every channel of the RGB. So for example, I'm going to select, I'm going to be working with the VV configuration. So for example, in the red channel, I'm going to put the image from the 19th of March during the flood. And then I'm going to put in the green channel, I'm going to put the image after the flood. And in the blue channel, I'm going to put the image before the flood. If I do so, and I click OK, I get my image. It seems some, well, okay. So this, I will explain you this difference in colors right now. Anyway, the important thing to notice here, you see that the flooded area has been highlighted very, very well by this very basic composition. So we can just zoom in and you can see the level of detail of Sentinel-1. By the way, we are talking about 10 meters pixel size. It is the highest spatial resolution you can get with Sentinel-1 in general terms. There are other options to get better spatial resolution, but that data is not that much available. again, I will not go into that. If you want to know more, send me a question. Anyway, what you can see is that the level of detail is very, very high. So you see, for example, the river is not highlighted as flooded area because it is actually not a flooded area. It is a permanent water body. However, all this area in green is the area that was flooded. And now the question is, why is this happening? I mean, why the river doesn't get highlighted while the area that was flooded, yes. I don't know if you have any clue, if you can think of a reason. If you want to send me your explanation, I will be happy to hear. If not, I will explain you what's happening. So just a few seconds in case someone wants to participate. Okay, let's move on. So what's happening is that if we have a look to the original images, so this is the image during the flood, this is the image after the flood, and this is the image before the flood. You can see that in terms of backscatter, in terms of the radiation that is going back, it is quite different. For example, during the flood, this area had a low backscatter, and after the flood, it had a very high backscatter. And before the flood, it was like in the middle. So these differences in pixel values when creating an RGB composition are of course going to highlight in different ways. This is like when you do an RGB composition in optical data. You are combining bands with different numbers, and the way the colors are formed affects, I mean, the pixel values affects the pixel value of a same pixel in 3 different layers will affect the way the color is displayed, right? So very basic. And that is why in our RGB composition, this area here gets a different color combination. Why? Because one of the images we were using, you see here, this one ends here, this one also, but the third one, the one before the flood, had a different cut. And when doing an RGB, well, you see that affects there is the third band has missing values for that channel, so the RGB composition is created in a different, the colors are created in a different combination, and that's what happens. So this is a combination, but of course you could do many more. I mean, you can play with the data as much as you want, and for example, we can do for the red channel the image before the flood. For the green channel, we can put the image during the flood, and for the blue channel, we can put the image after the flood, and we can just click and we will get a different color combination, right? So as you can see, a very, very easy processing step, let's say, for flood mapping analysis. It is very easy. You just need to pre-process your data, stack them together, and create RGB composition that you can later on export or send to your client or to your project, etc. However, this is only a first way to look at floods with radar data. Another way would be, another basic approach would be to do basic band thresholding. It means that we are gonna select a pixel value, and we are gonna say, on top of that pixel value, everything will be water, and below everything will be land. So we're gonna just do a mask. So before moving on and explaining you this, I think I got a question. So okay, so we have this question of someone asking if it's possible to combine 3 different images. So the question is it possible to combine more than 3 images together? Well, when doing an RGB composition, the answer is no. Why? Because there's only 3 channels that you can put together, right? RGB. There is no extra visible channel that you can play with. It is actually like how our eyes see, right? We see in RGB, we cannot see another layer. What you can do is false color composition. So you can change the bands that goes into red, green, blue, and produce different RGB images, but always combining a maximum of 3 different channels. That for sure. Let me know if you get the answer, if that clarifies your question. If not, I will go back to this concept later on. Okay, so as I was saying, another basic approach when doing flood mapping is to do thresholding. And in Snap, this is very, very easy. I'm going to be doing thresholding by using the image during the flood. So this image over here, I'm going to close it. So I'm going to be doing thresholding with this image because it's the one during the flood. And what's going to happen is I guess you can understand thresholding mechanism very easily. We set up a threshold and everything on top and below goes into one class or the other. So how to do thresholding in Snap is very easy. We just need to right click on the band of interest. In this case, this one, VV 19th of March, and we go to band math. In band math, we first of all set the name of the new band we are going to create. So in this case, I'm going to set a March 19 VV polarization, and I'm going to put the number 12. 12 is going to be the pixel value we are going to use to set the threshold. And now the question could be, why are you using 12 and not 6? Or why not 12.5? So this is a completely a good question. And why? Well, when doing threshold, there is no right value. It's something that you have to try. It's a trial and error process. I have been trying previously to this webinar many values, and I've seen that 12 gives me a nice result. And why do I know that? In Snap, if you go and zoom into an area, you can get to know the pixel value. So let's say you want to know the pixel value of a specific pixel. So you can zoom in a lot. Those are the pixels. And next to the product explorer, there is the tab pixel info. If you click on pixel info and then you move around the image, you will see that here in the bands tab, it is telling you which is the pixel that your mouse is positioned on, and the units, in this case intensity in decibels. So this is not actually intensity, it's the sigma naught. So you see, if I move around, I can see my pixels. So what's the deal here? If I move around the border area, I see values of minus, let's say, around 20. And in overland, I see values of minus 8, 9, well, more or less. Of course, this is a very small region. So the way to select a threshold is basically to move around your image, to move around the classes you want to distinguish, and see a little bit what are the distribution of the pixel values to just try. Of course, you will try once, and most probably you will have to try several times until you reach a value that is good enough. In my case, as I was saying, I identified 12 as the right value, so let's do it. Again, 19 March VV polarization and 12. This is just a name to keep track of what we do. Another relevant aspect in Snap is that when you create a band math, the band is not going to be saved directly in your computer. It is going to be created as a virtual band. It means that it exists, but it is an on-the-fly calculation being done by the software. If you do not want that behavior because you want to store that band and keep it for your own interest, you need to remove the option virtual. So remember, if you do not unselect this option and you close the software, the calculation that you have done will be lost. So remember. And then here we say, and here we write the expression that we want to set for this threshold. In this case, it's going to be larger than minus 12. So let's do this and have a look. So here's my band, and here's my original product. You can see that more or less it matches more or less the patterns, the dark patterns we see. But of course there is some noise in here. So if I zoom in, well, this is most probably noise, not flooded area. These random and little pixels around here. Remember, we are using radar data, which contains speckle, and this speckle changes the pixel value in a random way. We have done the try of reducing the speckle noise, but of course we cannot get rid of it, so there is still some random behavior, and applying a threshold in a radar image can be a little bit tricky because pixel values are not homogeneous. So maybe the threshold that you have selected is good, but still bad because there's this noise that makes that some pixels, even if they are not water, are classified as water, right? So, I mean, this is one of the disadvantages of using thresholding. One of the advantages is that it is very fast and very easy to implement, right? If you think about the application of flood mapping, what is relevant to the agencies or to the whatever the NGOs that are in charge of monitoring this disaster, they need a map. I mean, they don't care about very little spots that have been flooded. This is not relevant for them. They just want to know, okay, the flood ends here, you know, the borders, the area, if the village is more or less on top or not. So when working with Earth observation data, you always need to think about the application, how it's going to be used, and what's the added value that you want to bring to the final user. In the case of a flood map, as I said, it is not relevant to be super precise and to have the perfect boundaries of the flooded area. For some applications, yes, especially for urban floods. But for large floods like this one, it is not relevant. And that's why now what we're going to do is to clean a little bit this band by using very common GIS techniques. So there is a very common procedure in GIS for raster cleaning, for data cleaning, let's say, that consists of filters. So we're going to apply a filter in the image that is called open and close. So let's do it, and I will explain while doing it because it's going to be easier. To apply a filter, morphological filter in Snap, you need to right-click on the band that you want to filter and go to Filter Band. In here, you will access a huge list of filters. Again, if you are not familiar with this, I recommend you to just check on the internet. There's huge literature on this and different filters for different purposes. The one we want is opening and close. So let's do it, and I will, you will see what's the effect of this. So I'm going to select open 7 by 7. Let's do it and have a look. Here's the result. I'm going to close the previous images, and I'm going to do a very handy thing in Snap, which is combine two views at the same time so that we can compare. We go to Windows, Tile horizontally, and now we can see the two images at the same time. So what we have done with this filter is the idea was to close these little gaps, let's say, in our main flooded area. Again, for a flood mapping, this here doesn't mean that this area has not been flooded. If you think about the terrain, always try to put the image into the real world. Of course, this is noise. It's not a real spot of land that has not been landed, especially if all the surroundings around are flooded. So what we do is we run this open filter, which will take, and we are using the filter in a 7 by 7 configuration. It means that there is a moving window that goes around the raster, and for every pixel, it takes a 7 by 7 pixel window size. If all the 7 pixels are of the same class, of the same value, let's say water, or let's say 1, then the pixel that is being analyzed in the center of that moving window will be changed and will be open, right? And that's why we can, I mean, it's a little bit counterintuitive, and that's why we are closing, let's say, those little gaps by opening the raster, right? I hope it gets clear, and I hope the concept you get the concept. If not, please send me a question. So you can see that it works very well to close these very small areas, and this helps us to, let's say, homogenize the output. But of course, it has some side effects. If we go to the other part, we see that those very little areas that were identified as flooded areas, they have been now expanded. So you see, we've moved from this to this. So it is actually not ideal, because in one way we have closed the gaps in the main flooded area, and in the other part we have expanded the false positives, right? However, we can again use another filter to remove this, and to do so we apply a close filter. So we go to the band open, and we go again to filter, and we select closing 7 by 7, and we say okay. So what's going to happen here, it's the opposite, and let's put everything together. So here we have the original image on the left side. Here we have the open, and here we have the close. In this close, actually nothing changed, but if we go to the area where we have some problems, for example here, you see that in the original product on the left side we have small areas that were identified as flooded areas. In the opening we were, let's say, expanding those areas by using this filter. However, if we later on apply a closed filter, we are again removing all these little gaps in the other sense, and the result of this is that we end with an image that's a little bit cleaner. Of course, there are still false positives and false negatives. For example, those are most probably false positives. This is not a flooded area, it's just a pixel that went into our threshold and that has not been cleaned by our filters. But at the same time, we have cleaned a lot the main flooded area that we wanted to identify, so that we can send this information to the a little bit more clean, right? So here we get the result, and now we are ready, let's say, to play a little bit with the visualization of this. So what we can do is to play with the colors. For example, we can go to the slider, and I'm gonna just remove, I mean, this is just one way of doing things. I'm gonna create two colors, so either 0, either 1, and I'm gonna put water as blue. I'm changing here the color, and land I'm gonna put as none, so that I have a transparent mask. And what I can do now is basically go to my original product, the one, the original flooded product. I'm gonna close this. So this is my original measurement. And what I can do now is to overlay on top the flooded mask. So I can go to the layer manager in Snap, and I can just add this layer into the visualization by clicking on the plus button, go to image of band, and then I select the band. If you remember, we call it open 19 March VV12, open 7, close 7. So if I proceed, then I can look at the result and see how well it is matching from a visual perspective the flooded area that was identified in my product. Even you can play a little bit with the transparency, so we can play a little bit with this, or we can swipe and we can do like this, right? So you see, in some areas, in the main flooded area, it works very well. In some other areas, it doesn't work very well. Those are mainly limitations of the application we are using, right? We are using a super basic approach, which is thresholding. It is, I would say, the most basic approach. Still, I would say effective. If you think about flood management, let's say from the government perspective, they don't care that much about being super precise. They want a map, they want it as fast as possible, as reliable as possible as well. But this very basic technique will give you an output very quickly, and later on you can run more advanced techniques. What are other techniques? For example, classifications. If you go into classification procedures with algorithms, you will most probably produce maps that are more accurate. If you go to classifications which include machine learning techniques and good data, training data sets, the result will be even better. The good thing is that in Onda you have all the data. You can automatize the data retrieving because the data is present on the virtual machine. So you can automatize this. You don't need to download the image, wait until the download is done. So you can run things very operational in this kind of Onda environment. And if you know the steps, if you predefine your processing chain, you will end up with the result very quickly. Something you can do in Snap is to export the product. Let's say you want to bring it to a GIS server, and this is of course very easy. For example, in this is the water mask we have created, so we can right click on it and do export view as image, and you can save it, let's say in GeoTIFF. So I will save it as GeoTIFF. I'm gonna call it flood 19th of March. And I'm gonna select full scene and full resolution just to make sure that I export everything. And I'm gonna save it in this specific folder for convenience. So the image is being exported to GeoTIFF, and for example now what we could do is open it in another very common software like QGIS, which is again installed by default in the Onda VM so that you can start to use it straight away. For example, we can add a map from Google or from whatever provider you want, and on top of this we can add our GeoTIFF, and we'll just wait until it is saved. I think actually I have the backup product to show you. Okay, let's wait until it finishes, and I move on with the webinar. So while it finishes, this concludes, let's say, the application with Sentinel-1 data. So you see how with Sentinel-1 data you can derive flood maps very easily. You see the advantage of using DIAS. You have the data there, you just access it very, very quickly, and it's done. Okay, let's add the raster now that it's finished. There it goes. And now we zoom to the layer. Okay. This is the, sorry, I opened the wrong raster. Basically here you are seeing the multi-temporal RGB composition that we were talking at the very beginning. So this is one, let me add the other one, the one that I really wanted to open. This here, this one. There it goes. So here we see the, sorry for the, here we see the result, and well, you can, you know, it's QGIS. You can play a little bit with transparency, and well, you can play with colors, and you can produce maps, which is the important part. Again, you see that here we are identifying also water, and the ocean and rivers as the water mask. You could actually think about removing that because those are not flooded areas, those are permanent bodies, but again, it's up to the user to decide that and think about the best. So, as I was saying, this concludes the part of the webinar where we explain the processing of Sentinel-1 data. And again, I highlight what we did. We take the data directly from Onda, we skip all the download process, you can even automatize the retrieval from the cloud archive, and you can run operational processing chains to the data. Let's say every time there's a new image, I run my algorithm, I produce my GeoTIFF, I export it, and I publish it in a WMS server for the client. Something like that would be something very easy to implement in using the DIAS platform, using the Onda virtual machines. So once this is done, I can move to Sentinel-2 so that you get also an overview of how to use Sentinel-2 data. The Sentinel-2 part is going to be faster, it's going to be easier. We are good on time. So before moving to the Sentinel-2 part, I would like to ask you if you have any question about SAR, radar, Sentinel-1, the things we've done so far, because I'm going to move to optical, which is completely different, and I don't want you to keep any doubt in your mind. Again, if you have questions, if you are more comfortable with Italian, please ask your question in Italian. It's totally fine. Even if you want to talk to me, to Mario, or to the audience, you can raise your hand and I will activate your microphone so that you can share your opinion with the rest. Okay, so I will just give you a few seconds, and in the meantime, I'm going to prepare the Sentinel-2 layout. So what I'm going to do now is to close Snap, just to start with a fresh environment, just for that. So close here, and I'm going to close this window, and I'll just click the exit. So now we are with Sentinel-2, and let me actually introduce you to Sentinel-2. So Sentinel-2 is the second, it's another of the Copernicus missions. It is the main optical mission of Copernicus. And here we're talking about, again, a constellation of 2 satellites. We have the same configuration as with Sentinel-1. We have Sentinel-2A and Sentinel-2B. They are identical satellites in terms of their technical specifications, and they are orbiting at 180 degrees to each other for the same reason. When talking about optical data, the main characteristics are the number of spectral bands. In this case, we have 13 spectral bands that goes from the visible to the shortwave infrared. The other key aspect when talking about optical data, it's spatial resolution. With Sentinel-2, you get the highest spatial resolution available for free in Earth observation, which is 10 meters. If you want to go higher than 10 meters, you need to pay. So you see the advantage of using Copernicus data versus other satellites. And then we have a revisit time of 5 days at the equator. So you see, it is very good in terms of spatial resolution, it is very good in terms of temporal resolution, and also in terms of radiometric resolution, because it has many bands. And this will improve your ability to run analysis, in this case for mapping, but it can also be other things. So this is Sentinel-2, and now let's have a look to the data. Again, we are in Snap, and we start by doing the same, which is opening the product in Snap. For that, I go to the folder, or you can also go to File, Open Product, it's the same. And I navigate to the data I want to analyze. In this case, I have it here. Remember that this specific product you could also, it is also available directly from the Onda archive. Actually, I want to demonstrate this to you. Let's say this is the image of interest. This is the name, right? And that you have retrieved from the Onda catalog. And now you want to locate this image in the DIAS environment, in the Onda virtual machine. Again, right-click on the product and open RGB. So we'll just click OK, and now the image is gonna pop up. So in optical data compared to radar data, it is very easy, right? Because we can zoom in and we can relate what we see to the reality. It is very easy. By the way, I didn't say, but we're going to be running the analysis in an area over Iran. So we moved from Mozambique to Iran. Very recently, I think the 13th of January, there was a massive flood, a flash flood actually in Iran, and it was very notorious. So we are taking the chance to show you an up-to-date application of flood mapping. And well, you see Sentinel-2 images, they are 100 by 100 kilometers, 10 meters pixel size for the RGB and near-infrared band. And we can just zoom in and have a look. So again, very easy to interpret. In this case, we have a flood that contains water with a lot of sediments, and that is why you can see this color of the water. So those sediments are making the water to look like gray instead of, let's say, blue or, watercolor. Of course, image interpretation and a little bit of knowledge of the area always helps, right? We can think about the area as a very arid area. There's a lot of sand and loose parts that can go, and whenever there is a flash flood, it will basically, the water will take everything with it and it will go down the stream. So the main area, the main flooded area, you can see it here. Oops, sorry. Yeah. So all this area is a flood. So with optical data, it is much easier because there is no need to pre-process the data. The main pre-processing step that is required with optical data is what it's called atmospheric correction. And atmospheric correction refers to the fact of moving from top of the atmosphere reflectance values to bottom of the atmosphere reflectance values. If you are new to optical data, just to make sure we are all at the same level, optical satellites measure reflectance, which is a physical concept, right? We have the sun sending radiation, hits the target, goes up, and we have reflectance, etc. The satellite is measurement top of the atmosphere reflectance. It means that the radiation goes through the atmosphere, there it interacts with the atmosphere, it changes, and the satellite is measuring the result of that interaction on top of the atmosphere. However, for remote sensing analysis, what you want is the reflectance that comes from the bottom of the atmosphere. It means the reflectance that was coming out of the target that was sensed. Let's say you are sensing a crop. You are not interested in the reflectance after the interaction with the atmosphere, but the reflectance that result of the interaction with the plant, because this will give you insights of the status of the vegetation, etc. Right? So that's why we run atmospheric corrections, which are algorithms that use atmospherical models about the composition, status of the atmosphere, etc., to correct those reflectance values. Luckily enough, ESA is delivering sentinel-2 data which are already atmospherically corrected. So you can skip the atmospheric correction step. So imagine you are in the DIAS environment, in the Onda environment. You have the Copernicus data, the sentinel-2 data, which is even already with the atmospheric correction. So you are literally ready to start. I mean, you can take the image and start to run whatever application, flood mapping, crop mapping, or whatever. So this is really a change in the world of Earth observation, and with a platform like Onda, you can really improve your ability to produce added value services. So we have the Sentinel-2 level 2, so level 2 means atmospherically corrected, and we can run a very basic analysis, which is going to be the normalized difference water index, the NDYI. So, sorry, not Y, totally. You might be familiar with NDVI, which is the normalized difference vegetation index. In this case, we're using the normalized difference water index, which makes use as NDVI of the difference in reflectance of water in two key spectral bands, which is the green and the near infrared. So if you look at the spectral band of water, you will see that at those specific spectral bands, there is a sudden change of reflectance from water. And by using this to derive an index, we can highlight the presence of water very easily. This is the same as NDVI. I mean, the approach is the same. Again, you see we are using a very simple approach, which is deriving an index. We are not going into classification, machine learning. I mean, you could, and this is totally feasible in Onda, because the VMs are powerful enough. But what I want to highlight is the fact that using basic approach can give you a first result, which is good enough for a quick response, and then you can refine your processing later on. So, for those of you that are new to this concept of the normalized difference water index, the normalized difference water index is the most appropriate for water body mapping among the different indices that are available. So a water body has a strong absorbability and a low radiation in the range from visible to the infrared wavelengths. And the index, as I said, uses the green and near infrared bands of remote sensing images to highlight that. So it is also actually sensitive to build-up and length, and often, you need to know the limitations of the index to interpret the result. So how to derive the index in Snap is very easy. We go to optical, because now this is an optical image. We go to land, and then water radiometric indices. And then we have the NDYI, the normalized difference water index tool. You could potentially run this graph, this index by deriving, by doing band math, right? Because you can create a band, edit the expression, and here you can write the formula of the index. However, in Snap you have the specific operator for this index already available, so I think it's just easier to do it like that. So again, we have this common structure of the operator in Snap. First of all, the input and output information. We save it with the default with different suffix that is attached to the original name of the product, and then I'm going to save it in this folder as default. The processing parameters, there is basically nothing to change except from the fact that you need to resample the image. So remember, Sentinel-2 products come at different spatial resolutions. I said before that you have 10 meters pixel size, but those are only for specific bands. The other bands are at 20 meters pixel band. Sorry. So you see here that the red, green, and blue and the near infrared bands are at 10 meters. Those are 2, 3, 4, and 8. Those are the numbers of the bands that are at 10 meters. The other bands are at 20 meters. And then we have 3 spectral bands, 1 and 10, that are used for atmospheric correction and that are delivered to the users at 60 meters. However, this doesn't matter because those bands are not intended for any land application. They are intended for only the atmospheric correction. So we don't need them. So remember, when working in Snap with Sentinel-2, you have to know that most of the operators require the product to be resampled to a common spatial resolution. Because we have bands at different spatial resolutions, 10, 20, and 60, you need, first of all, and this is very common, first of all, to resample to wherever resolution you want. I would recommend you to always resample to 10 meter pixel size, because in that way you will not lose the highest level of detail available in an image. If you go from 20 to 10, you are not losing spectral information. If you go from 10 to 20, you are losing that level of detail. So that's why here I select the highest resolution. Then you can select the upsampling method in case you're interested in that, but it's not going to change. And then you need to specify which are the bands that are going to be used. Since we are using this operator, it already recognizes which are the bands we want to use, and we just run the process. Actually, okay, as you can see, it takes a very takes a few seconds. Remember, resampling and deriving of the index is happening right now, so you see it's very fast, and this is mainly the consequence of working in the Onda environment. So we will see now the results, and now we can close this and have a look at the result. So the result is added to the Product Explorer. We go to bands and we open anyway, and we open the index. So as you can see, water gets highlighted very, very well using this ratio. And now what we can do is the same as we did before. We can just do a threshold, because the values of the normalized difference water index, as with NDVI, go from minus to +1. Since we are only interested in the flooded area, we can just do band math. And we can do, for example, we can call the band floods 13th of March with Sentinel-2, for example. We want to save this as virtual, and we say the index has to be larger than 0.5. And now how to select the threshold? Well, let's actually do it like that. We can go, for example, to this area. We can go to the pixel info, as we did before. We navigate over the area, and we see that water has values of 0.9, well, very, very high values, right? So when selecting the threshold, you can take this information. So let's do it again. Floods, 13 March, Sentinel-2, and I'm going to put the threshold of 0.85, for example. Avoid the point here, 0.85. And here we say 85. So let's remove the virtual option and click OK. So here we get the mask. So this is, in the end, we end up with the same result as with Sentinel-1, a water mask. The difference is the steps that we have done to arrive to get to this point. With Sentinel-2, it is much faster. With Sentinel-1, there is other things to do. However, you have to think that when there is a flood event, most of the times there are clouds, because there is a storm, there is a cyclone, a hurricane, whatever. So most of the times when working with floods, you will see that optical data, although it gives very nice results, because you don't have all this noise, speckle, etc., most of the times the imagery is not available. So the only solution is to work with Sentinel-1, and that's why we wanted to show you the application with Sentinel-1 data, because when working in this domain, most of the times, if you want to provide reliable data, you will need to work with SAR data, because in that way you know that the image will be there and you will be able to run your application. If you only rely on optical data, if there are clouds, you are done. So again, let's do the same. I'm gonna just produce the mask. I'm gonna remove the slider. I'm gonna change the colors, water blue, and the rest is gonna be transparent. And now I can just go to my original image here and, for example, add the mask. I do so by going to the layer manager, then clicking on the plus button, and then image of band, next, and I select the floods. And here it gets added. And now you can play with transparency. Well, again, you can see the swipe. Again, remember this is a threshold, so even if it's optical data, there might be some noise because the threshold is very you mean it's measure. We split the image in two, and for the majority of the case it can work, but in some other cases it can't. Again, other techniques, more advanced techniques, will help you to get better results. But again, you can see that with a super basic approach, you can get very nice results. Again, as I said, you can export this image as GeoTIFF, for example, so that you can open it in another software. For example, here I'm going to call it floods Iran 13 March with Sentinel-2. And now we can, as we did before, open QGIS and get to see the result. So that would be the analysis we wanted to show you today. Let's finish it by showing the result. And now the result. There we go. Okay. So, well, this is just to show you that you can overlap the results from Snap in GIS softwares, etc. You can even download things to your local computer. Let's imagine, I mean, a typical way of using the cloud is, for example, run all the heavy processing on the cloud and then download to your local computer the final layer, the final image, the final PDF that contains the map. Because in that way you can work with a very, let's say, regular computer where you don't have to do any huge investment, you don't have to upgrade your computer every year or whatever. And then you do all the heavy processing that only requires a light internet connection to access the cloud. You have all the software, all the RAM available. If you need more or less, I mean, Mario will come back to these concepts now. How to download something from the virtual machine to your local computer? It is very easy. In the implementation of the virtual desktop we are using in Onda, you need to type in your keyboard Ctrl-Alt-Shift. All this information that I'm telling, if you have questions, I'm sure you have our email, so you can contact us, so don't worry. So it's Control Alt Shift. I can maybe write here so you see it. Control Alt Shift. This is the key combination that you have to press at the same time. So Control Alt Shift, and then this side menu will pop up. In this side menu, you can navigate to the different folders of the virtual machine. So here you can access all the folders. And for example, I can go to the one I have created for this webinar, and I can download the GeoTIFF of the floods in Iran. I can just double click on it. Now the file is being gets ready by the virtual machine. And once it finishes, you will be able to download this to your local computer. Maybe I can show it with a lighter file. For example, if I want to download this one, so what happens is that the file gets, let's say, it has to be prepared to be downloaded. So that's why we see here this process being run. And once it finishes, you will be able to click on it, and the image will be downloaded to your computer. I will just wait for this to finish, and I will show it to you. So that's all from the analysis. I just wanted to show you the very last slide so that you remember the difference between optical and radar data. When working with optical, remember that it is very easy to interpret the image and to run analysis. For example, here we have an image of Sentinel-2, and this is a single band, so we have gray colors. And you can see that just looking at this, you can already recognize different patterns, the crops, etc. If we do a simple RGB composition, this gives you the ability to even differentiate more things, and it's very easy. Visually, you see everything. However, if we go to radar, if we look at the same area with radar, this is how it looks like. So you see, it is completely different. You cannot use your same concepts to analyze a SAR image versus an optical image. But actually, this is not the original image, because the original image comes like this. And that's why we have to run all this pre-processing that I was showing before. So remember, with SAR data, you need to do some pre-processing. The pre-processing that we have shown today, let's say, it's kind of a standard that can be applied for many applications. And in the case of flood mapping, you have seen today that it is very easy once you know the steps. So now we're going to move to the Q&A session. I will give you some minutes for you to send your questions and ask the last things you want to clarify about SAR, Sentinel, the Onda VM, the cloud environment, etc. So I will give you a few minutes. Please send your questions now, and we will be back in 2 minutes with the answers and the closing part of the webinar.
Okay, so while we wait for your questions, so I really want to thank you all the attendees, for staying with us for the whole webinar, and also want to thank Miguel for the very clear and also complete, in my point of view, webinar, because we saw examples with both optical and radar sensors, so that you can have with you a picture or an example, at least, of flood mapping applications using the two technologies, radar and optical satellite data. So our goal, as said, was to show you how you can use Onda DIAS platform for flood mapping applications. So Onda is a platform that you can use to develop your applications, your idea for your next Copernicus Hackathon in Vicenza. So you can develop your idea. And if you are interested in using Onda during the hackathon and also during this month in February, I know if you are already aware, but there are some Onda virtual machines available for you, so you can get free access to Onda virtual machine for free for the entire month. So if you're interested, please contact your your organizer of the hackathon, and we will give you access to our virtual machines, and you will be able to use them for the entire duration of this month. But of course, our relationship can go beyond also the hackathon, because if you have an idea of an application that you want to develop, or a service, anything that you want to develop in a cloud environment, don't miss the opportunity to use this very powerful platform that was designed for applications based on health observation data, because again, the main advantage is that you have direct access to almost 22 petabytes of data, and all the new data that is acquired is made available into Onda on a daily basis. So if you're interested, you can find additional information on our website, but please feel free to also to contact us. We also have a service desk that you can contact in our from our website in the tab Contact Us. So you will also find some documents in the website regarding the use of Onda, the APIs, the catalog, etc. So the information is there, and we are available now and also after this webinar to answer your questions. So let's see if you have some questions now. Please feel free to write them down, or also to raise your hand, your virtual hand at least, and so that you can speak with us and with the audience. Okay, we don't see questions for the moment, so please, these are our emails, our contacts. Please feel free to send us your questions if you have. And again, thank you very much for your time. Thank you for being with us. We hope that you enjoyed this webinar. In my opinion, it was very clear, and so thank you again, Miguel. So please keep in touch again if you're interested in using Onda for the purpose of the hackathon. Please contact your organizer so that we can give you access to the virtual machine. And also, if you have other ideas to develop and you want to develop them into a cloud environment, feel free to contact us, and we will give you all the information needed. So thank you very much. Keep in touch, and we wish you a very pleasant day. Bye.